After all, the same mathematics which predicted the orbits of the planets also governed the firing of artillery. The mathematics of ballistics told them exactly where the shells would land.
Of course, at the beginning of the 20th century, ballistics was essentially firing at a stationary object. And you might have to fire over something, so you might not be able to see what you were firing at. So the mathematicians had sort of sorted it out. They had range tables and so on.
The magic of science, this predictability of things through mathematics. Science is not just proving theorems, it's to give us some power over nature about what happens, predicting an eclipse, this kind of power. Building steam engines is also power, and science was built in part about that.
The tragedy of the war was that no matter what carnage unfolded, they believed there was not only a science of ballistics, but a science of war, a way of predicting how many men per mile of front would win the objective. They thought if they understood the science of war, they could control its outcome. They could simply overpower the chaos. In the end, they weren't fighting each other. Both sides were fighting the chaos of reality. In the end, the chaos defeated them all, and 10 million men died. Poincaré's notion that a small, unnoticed disturbance could eventually cause an unstoppable storm was the first discovery to tell us the world is less predictable and controllable than we'd like it to be. One of the mathematical roots of modern anxiety. The second was uncovered in Russia by Alexander Lyapunov. He was studying the transition from stability to instability in fluids, but doing so during the great upheavals of World War I and the Russian Revolution. Lyapunov was studying the way a fluid or gas becomes turbulent. It was one of the most intractable problems in all of physics, and he was trying to put a number on that transition from order to chaos. He was trying to understand how systems seem to maintain their order, almost resisting change, but then reach a critical point at which they seem to flip suddenly from smooth to turbulent, from order to chaos. What we now call tipping points.
This move away from the idea that the world is ultimately predictable to one where it's unpredictable is mostly associated, at least in the climate and environmental world, with this idea of a tipping point. So this idea that you push the system and it goes, basically, how far it moves, how far it changes.
Professor Peter Cox is one of the UK's top climate change experts and an advisor to the government.
In that case, you imagine a system, say you're rolling a ball up a hill. You know, if you roll the ball up a hill here and you let it go, it's going to go back down this way. But say there's a peak on the hill, you roll it up so far at this point, it can go either way. And then, of course, if you're at the top of a hill, you can push it an infinitesimal amount and it'll be off. And there's no relationship between the ultimate displacement and how hard you push it. So it's essentially an unstable system.
Lyapunov's work had begun to put a number on this moment of instability. The moment when the ball at the top of the hill is pushed over, when the orderly plume of smoke suddenly becomes turbulent.
Most people, when you ask them what is dangerous, is falling off a cliff, right? I mean, and that's the equivalent of a tipping point, right? It's where the system changes and you can't go back.
But while Lyapunov was still trying to understand instability, his life was approaching its own tipping point, when the chaos of the Russian Revolution and World War I overwhelmed him personally. Tens of thousands of war wounded had been pouring back from the front and brought with them an epidemic of tuberculosis. When his wife became infected, Lyapunov tried desperately to save her. But on October the 31st, 1917, she died in his arms. Hours later, the same day, he put a bullet through his brain. Poincaré had discovered that our world might not be as predictable and controllable as we had thought. Lyapunov's work had put a number on the moment of transition from order to chaos, and opened the door to the modern idea of the tipping point. Between them they had discovered what could have been the beginnings of a new and profound understanding of the world. That chaos is a part of the system, not just its breakdown. But Lyapunov was dead. Poincaré never took his work any further, and the rest of us, we wanted only to believe that chaos and unpredictability were just a nightmare from which we could wake. We stood at the place where a clearer understanding branched off, but we did not take it. The war had shaken our old faith. Somehow it had to be renewed. And to do that, a new icon of belief had to be found. Henry Ford's assembly line was that icon. It became both the symbol and the means by which we believed we could engineer a world of stability, predictability, and prosperity. We began to see the world, particularly the human world, the economy, in its image. No longer a world which might veer out of control, but one perfectly balanced, stable, at equilibrium, which had the dependable and changeless nature of a machine.
And they fell back to classical physics, to equilibrium systems, where, if you like, there is a fixed amount to spread.
Professor Paul Ormerod was for a decade Director of Economics at the Henley Center for Forecasting, and is today a respected author and consultant.
And they use the mathematics of that to try to explain and account for a very elaborate theory of how economies would actually allocate resources in a most efficient way. But it was a fixed set of resources they were concentrating on, and an equilibrium concept which they borrowed from classical physics before Poincaré made his discoveries.
Once we had imagined the economy as a machine, it was a small step to believe we could engineer it, maybe even control it.
The idea of an equilibrium system became really quite embedded in economics as a description not merely of the market economies of the West, but also of an idealized centrally planned economy running like a machine in complete equilibrium.
And for a while it worked. In the roaring 20s, the cars rolled from the assembly lines, and the tractors ploughed the land.
Once again, the ploughman followed the herder, and the pioneer came to the plain.
A wave of optimism flowed from the factories and fields of the new world.
We had the manpower. We invented new machinery. The world was our market.
And we seemed to be back in control. But only for a while. We may have wanted to see the world and the economy as a machine, stable, unchanging, at equilibrium. But how we wish the world to be, and how it actually is, are not the same. This is the massive Fisher car body factory in Detroit. Once it was part of the seemingly indestructible US auto industry, part of the good times, which we thought would never end. But in 1929, they did.
But the winds still blow and the sun still bakes the land. We must practice control and conservation if we are to save the rest of the grass.
Without warning, the world reached not one but two tipping points. The climate and the economy both lurched without warning, without obvious cause, from equilibrium to chaos. The nightmares of the Great Depression and the Dust Bowl were upon us.
The Great Depression of the 30s was a major problem for equilibrium economics. The market for labour, for hiring and firing people, wasn't in equilibrium because 1 in 4 people didn't have jobs.
And yet even this was not enough to get us to give up our faith in the world of order, equilibrium and control. According to the equilibrium view of the world, there couldn't be anything inherently wrong or unstable with the economy. people themselves must have caused the breakdown.
But the basic argument, and it still remains the same today, is that people were, in a sense, weren't really involuntary. They weren't unemployed because they'd been sacked. They were choosing to take, it's incredible, but this is true, they were choosing to take leisure and be unemployed rather than work. That was the core of the explanation, that people were making a rational choice between consumption and leisure. So essentially the Great Depression was essentially an extended holiday for tens of millions of Americans. But certainly many major academic economists, including some Nobel Prize winners, subscribe to this theory.
The experts at the time found it impossible to imagine that the Dust Bowl or the Depression were in part caused by inherent instabilities or tipping points in the systems themselves.
Another decade of reckless use, the grasslands will truly be the great American desert.
There were no tipping points. The cause, we decided, was reassuringly simple and mechanical.
I think when we were thinking in a more linear way about the world, we tended to look for causes that fitted outcomes. Actually, if you're talking about instability, of course, I mean, say you've got a pencil balanced on its end, doesn't really matter which breeze blew it over, something was going to blow it over. So you could say, well, that particular eddy caused this thing to tip, but really the only thing that matters is it was going to tip anyway. It was unstable. And then, so when you get to the view of the world having these bifurcations, tipping points, then in a sense, the causality is less critical. It's just that the system is going to change.
But while we were adapting to changes in environment, we paid the price of feeling insecure.
Despite all the chaos and turbulence of the 30s, despite the blighted lives and misery, economists and scientists continued to see the world as they always had, believing that the uncontrolled would one day be brought within our grasp. It was the invention of the computer at the end of the war which suddenly seemed to promise a level of understanding and control we had never had.
再回答一下大家的一些问题啊。我在 Tech 用的导师呢叫做 Omri Barak， 在计算神经科学这个领域呢，实际上非常少有人能够发表 Nature Science 的论文，而我的这个导师呢就发表了2篇。实际上在他发表第1篇论文，当时是在 Nature Science 领域第一次有计算神经科学的这种论文发表，就是他来发表。所以说其实他在对于用机器学习来解决神经科学的一些问题上是有非常独到的一些见解的，他也是一个 RNN 领域的一个专家。所以我觉得这部分内容大家也可以多关注一下，我会把他一些思想介绍出来。不过我觉得最重要的还是大家先打好基础，下午童校长的课非常值得期待，希望大家去了解微积分的奥妙。还有什么其他的问题吗？其实我的经历的话，其实我在以色列理工之前，我在巴黎高师之间，我还在香港的一个叫浸会大学的一个学校。虽然这个学校本身可能大家并不太了解，但是它的非线性科学中心是亚洲这个领域都是非常前卫的一个地方，就是它中国的这个非线性力学这一块是从这里发起出来的。然后我在那里学习的知识包括就是说了解用非线性动力学的一些手段来解决神经科学的问题。